Hey, time for part 3. Last thing was a little bit about refraction, and just to give one more example, if you have, let's just say some water, and some light is going to be hitting the water, and when that light hits the water, it's like a little car. And when the car hits the water, in this case, the front left tire is going to hit the water first. That's going to slow that tire down and it's going to turn it like this. Now, if you have light that's of a particular wavelength like that, and then you have some other light that's, let's see, a shorter wavelength, the shorter the wavelength, the more sharply the car is going to turn. So that light would maybe turn that much. And if you had an even longer wavelength like this, it's not going to turn much at all when it goes into the water. So the shorter waves like violet, those refract the most. Longest waves like red, those refract the least. And they always turn toward whatever's more dense, like the water. Now, just for the heck of it, if you have something coming out of the water, think of it this way. Let's say some light's coming out of the water like this. Same thing will work. This is the H2O, this is the air, and light travels faster through the air. Think of it as a car. Now, as it's coming out, this tire is still stuck in the water. It's going to be moving slowly. This tire is still is now in the air, so it's going to be going faster. This is going to go faster, this is going to go slower. That's going to make the car bend to the left. So it doesn't really matter if light is coming into the water, it's going to bend like that. If light's going out of the water, it's going to bend the same way. So just always think of it, when it enters the water, it turns toward the water. And I guess when it comes out of the water, it actually turns toward the water too. It doesn't ever go farther away. So it's always moving toward whatever is more dense. All right, moving on here. Fish. So you have this fish. It says the eyeball is looking at the fish. We have a fish and an eyeball. It would like, so the eyeball wants to shoot the fish. Let me put a little nose on it and a mouth. Here's a person. Now we've got a person. The person would like to shoot that fish. The problem is that the eyeball sees the X in a place that is really not the true location of the fish. So the eyeball does not see the X here. This is where the fish really is. Draw the X where the eyeball sees it. In order for this to work, or in order to do this, we just need to remember that the light that's traveling from the fish to the eyeball is going to bend. You could think of the light going from the eyeball to the fish to the eyeball. It doesn't really matter. What it's going to look like is something like this. Like that. So either the lights, you can think of the light coming from the eyeball, hitting the water, turning toward the water, or you could imagine the little car down in the water. This wheel comes out first, it's going to go faster, this one's going to be stuck in there, that's going to turn it this way. Whatever the case, light travels like that. So if light's traveling like that, things are going to look distorted. Our eyes don't usually expect light to be curving. We think of light as coming in a straight line. When you look at this paper, you're thinking that light is coming straight from that little R in the word denser right to your eye. So when you look through a tank of water and you see light that's actually curving, you don't think it curves, so you get confused. What you think is that light travels in a straight line. So you would think that the light would be doing this. I'm just continuing this straight line to the eyeball because that's what we automatically assume. So even though really this light is coming from the fish down there, we think the X is right here. And we would think that the whole fish would be somewhere up here. So draw the X where the eyeball sees it, show the path of light traveling from the X to the eyeball. I've done that. This solid line, that's the path of light. That dotted line, that's where the eyeball thinks the light's coming from because we expect it to come in a straight line. So if you want to shoot a fish, where should you aim? This is where you see the fish. If you shoot at the fish where you see it, you're going to miss it. You're going to shoot above the real fish. So if you want to hit a fish, you need to aim below where you think you see it. If you think you see it here, then you need to aim somewhere down here, and then you can hit the fish. Where should you aim? Below where the fish appears to be. That's how you shoot fish. Now we get to rainbows. Let's see if there's this diagram. I think I've got another picture of a rainbow. Yeah, there's a rainbow. It's not, the colors are not very good, but you can see the reddish end over here and then greenish stuff in the middle, and then it gets bluish over there with the blue sky behind. But the point of these diagrams is to explain why a rainbow looks like that, what's causing a rainbow. And the explanation lies in a couple of internal reflections and also refractions. So if the sun is somewhere over here, and this is your eyeball, and there are these water droplets, there are 3 water droplets up in the sky. The sunlight, this would be light coming from the sun, it enters each of these water droplets. Each of these arrows that I'm darkening right now, that's the sun going into the water droplet. And sunlight has a lot of the different, well, you could just say all the different colors of the rainbow in it. It's not exactly white, but it has the colors of white light, and it probably has more yellow than some of the blue end, because the blue stuff gets scattered through the atmosphere, like I mentioned. Some of the blue does make it through though, because you can see a blue in a rainbow. And we can see blue if you wear blue, so not all the blue is getting lost to the sky. All right, number 15. When sunlight enters the raindrops, it gets refracted. So right here it enters and it's getting bent right there. That's refraction. The eyeball below sees a rainbow of colors when it looks at the raindrops. Label the rays of light exiting the raindrop in with their proper colors. Choose either red, blue, or green. Before I do that, I want to say that right here, there's reflection happening. So there's refraction, which is bending. The light goes into the raindrop and then it gets reflected off the back of the raindrop. Some of it probably goes out the other side, but some is reflected off. And then that stuff that's reflected bounces over here and it goes out of the raindrop and it refracts again. Now, as the light goes in, white light goes in here, and all the different colors come out there. I've only shown 3 just to keep this simple. So if I had to choose red, blue, or green for each of these, all we need to know is which one bends the most, because the one that bends the most is this one. This is going in and it's taking the sharpest turn. This one over here, that's bending the least. So whichever color bends the most is that one. Whichever color bends the least is that one. And if you can remember that this kind of wave is like a fat car, which turns the most. This kind of wave is like a skinny car, which, this is the fat car, which turns the most. This is like a skinny car that turns the least. You can remember it. This is like red light. Red turns very little. It doesn't refract much. The bluish end of the spectrum, that refracts more. So when this light comes out, the one that bends the most is going to be that blue. This is the blue. This is going to be the red, and this is going to be the green. Now, the white light does the same stuff going through this raindrop. Exactly the same thing happens. The color that bends the most, that's the blue. The color that bends the least is the red, and then green is in the middle. And then light goes through this raindrop, and it does the same thing. This is where the blue comes out, the green comes out in the middle, and the red there. Now, here's why you see the rainbow. This really doesn't explain it all yet. When you look up into the sky, if this is your eyeball, I'll give you a nose again and some hair, nothing else. Maybe a chin. Okay, you got a chin. Eyeballs coming out your mouth. So you look up into the sky and you see all these raindrops, and the sun is at your back, and the sun is shining on these raindrops over here, and it's refracting and reflecting, and the colors are coming out. When you look at this top raindrop, you don't see this blue, because that blue is going over there. It's over your head, and you don't see the green. What you do see is this red. You're seeing this particular bit of red coming out of this raindrop. So when you look at this raindrop, that looks red. Doesn't look blue, doesn't look green, you don't see any of the other colors. It's perfectly positioned so you see the red. Now this raindrop is lower down, so the red that comes out of it, it winds up below your eye. The blue winds up above your eye. It's the green that actually hits your eyeball here. So this raindrop, you just see green when you look at it. This lower raindrop, the red goes below you, the green goes below you. It's the blue that actually makes it to your eyeball. You see that blue? So this raindrop appears to be blue. And there are other colors in between red, green, and blue. There's orange and yellow, and indigo and violet down here, but I'm just simplifying. So when you look up into the sky and you see a rainbow and the sun's at your back, there's this rain happening over on this side of the sky, you're going to see a rainbow with red on top, the bluish violet stuff on the bottom, and green in the middle. This is a better diagram of what I was just telling you. So showing the same thing, it's showing refraction here, refraction there, reflection there. There are also double rainbows where you actually get two internal reflections, but we won't get to those later. This is showing some of the sunlight being reflected off the raindrops, so not all of it goes through. They don't show this, but some of it goes out the back of the drop. But notice that all the colors turn. The sharpest turn, that's the blue end, that's the violet. And the least sharp turn, because there's less refraction, is the red end. And that red end is perfectly positioned for this guy to see it. All the other colors go over his head, so he sees this raindrop as red. This lower raindrop down here, all these other colors go below him. He sees the violet end. And there would be raindrops in the middle. It would be orange, yellow, green, blue, and indigo. So that's why a rainbow is always going to have red on top, and then the violet stuff on the bottom, and the green in the middle. Let's see what's next. Ooh, there's a crazy guy doing something. We'll get to that in just a second. Okay, so number 16, use your knowledge of refraction to show how light's bent as it travels through a lens of a magnifying glass. You probably already know what happens when light goes through a magnifying glass. If this is the sun over here and sun's rays go through here, you know what's going to happen, but let's just think of it in terms of refraction and little cars. So if I have a little car right here and a little car over here, and this is glass and this is air, when this car hits that glass, the part in the air, this tire right here is going to be going faster, but this tire that hits the glass, that's going to slow down. So that's going to turn it this way. Opposite thing's going to happen over here. This left front tire is going to hit the glass first. That's going to slow it down and turn it that way. So the light's going to go through like this. And then when it's coming out, kind of the same thing again. The left front tire is going to stay in the glass longer. The right front tire is going to be out in the air. It's going to go faster. So if this one's going fast, this one's going to slow, that's going to turn it again. Same thing here. When it goes out, it's going to turn like that toward the glass again. Think of it as a little car. This one's stuck in the glass, this one's moving fast, so it's going to go like that. So that's what a magnifying glass does. It takes rays of sunlight and it converges them. It's called a converging lens. Okay. Now we get to reflection of light. I don't know what I did with it. I used to have a mirror that I took out of a flashlight. If this were a flashlight, you can unscrew the end of the flashlight and take the mirror out. And all I have right now is really nice flashlights where I don't want to break them apart, so unfortunately I can't do this. But the way the mirror works, this is about reflection of light, is that the bulb, this is the bulb, gives off light in every direction. It radiates light all over. So light goes to the left and to the right and up and down. So if you just have a bulb, it'll light up the whole room, but it won't give you a nice beam. And what the reflector does in the flashlight, it's designed perfectly. It's got just the right kind of curve so that when light goes out like this, it reflects like that. When light goes out here, reflects like that. When light goes over here, it reflects like that. All these reflections end up being parallel. So what you get is a nice flashlight beam that just goes out in a straight line, and you can shine it on things. Now, the second part of this says, show how you can use a flashlight mirror to start a fire. If you take this flashlight out, you can reverse the process. You can have sunlight shining in here on the mirror, and when it does that, it'll bounce off and it'll go up here somewhere. And sunlight hits the mirror there, bounces off and goes there. Hits it here, bounces off there. All of these rays converge on this one little spot. If there's usually a hole in the back of the mirror, you can put a piece of paper through there, black paper or something, and it'll heat it up and burn it. This is a picture of a guy. Oh, I'm almost out of my battery. So this is a picture of a guy who's made a really big one of these, and he's a hippie kind of guy. He's made a giant parabolic mirror, and he's cooking something with a pressure cooker. This is same kind of thing, but it's using sound. And there's somebody down there who whispers. This is called a whisper dish. They whisper, and the sound reflects off of that dish, goes in a straight line to this dish, and then gets concentrated for somebody else to hear. There's a nice diagram of the whisper dish, just showing how if one person whispers right here, the sound goes off, bounces over to this dish, and then gets focused again by that person's ear. And this is an actual whisper dish. This girl is whispering into this hole, which keeps her mouth in just the right spot so she can send her sound to the other end of the field. See if there's, nope, nothing left. Okay, I think we've gotten to the end. Seems like I was going to say something else, but my battery's out. That's all.